Recording. How about that? And I say, hello. Hi. Yeah, not rhetorical. Actual hello. Yes, waving is good too. Happy Garbage Day, everyone. I know. It's not a thing. I had a student ask me that earlier. Is that a thing you say? No, it is not. It's just a thing I invented because it helps me keep track of which day it is. In pandemic central time, every day is pretty much the same except for the 2 days I teach, and then I got to keep those two straight, and I know if it's garbage day that I say have a good, I'll see you Thursday. And if it's not garbage day, I say have a good week. That's how I know. But what I do want to say, to start with here, sharing my screen so that we can all be on the same page quite literally, is homework. So I asked a few minutes ago, but I'll do it again. Any questions on homework 4 that is due tomorrow night? As a reminder, this follows the last 2 models of example 3, which I updated the handout and the code to make it easier for you to get partial correlation effect sizes. So I had made it a little bit convoluted before, and now I have additional code that makes it so that you can lump together the fixed effects that show up out of the model with additional linear combinations that you ask for specifically and get effect sizes either way. So I would refer you to those resources in helping to get those questions. So, no homework questions? Okay, that's fair. I'll shut it down. I've gotten a few folks asking me about taking classes since registration for fall has opened up. For anyone in this class, the next sets of classes, if you're interested in going further in quant methods, I would recommend is design of experiments in the fall. That's 6246, I think. And after that, the next one I would recommend would be back with me, generalized linear models, 6270. In your programs of study, it is likely not included because it just got approved as an official course last year, so it's a new listing. But I developed it specifically as a follow-up to this course. So it's designed to be the next one. If you have any questions about what would be best for you individually to take based on your research, I'm happy to chat with any of you about that as well. But for now, we get to talk about regression models with multiple predictors. I think that's what we're talking about, right? That sound vaguely familiar? Yeah? And we left off with the idea of this model, which we all agree, had I shown this to you on the first day of class, would have made nearly everyone drop and or cry, you know. But now we're ready for it. It's April, right? We've come a long way since then. So we are building towards the grand finale of the idea of evaluating competing effects of multiple predictors for the same quantitative outcome at the same time. And nothing has changed with respect to how we talk about what a slope means and how we would put predictors of different kinds in the model. What has changed is how we think about their contribution as unique instead of bivariate. So this model that I'm on, let's see, page 6, this is example 4A. This model was introduced in pieces. Am I recording? Let's always check. Yes, I am recording. Thank you for asking me that. Sometimes I forget, and then I'm really mad at myself because you know what happens if I forget to hit record? I have to do it again. Yeah, because I made a deal that I would do this. And so, yeah, if I'm not hitting record, I just create more work for myself. So yes, I am recording, thank goodness. So we introduced this particular model in pieces. As promised, this will be the last time that we're predicting income. I have a whole new example with a different data set. And so income is our quantitative predictor. We are examining the effects of, or income is our quantitative outcome, sorry. Need to calm it down a notch. We're examining the effects of 3 predictors conceptually. So these 2 terms right here, beta 1 and beta 2, those are attached to indicator dummy codes. So they are representing the idea that we have a reference group and we're asking about how each of the other alternative groups differ relative to that reference group. And in this particular variable, it is self-reported working class, low, middle, or upper. So I designated low as the reference, and I'm evaluating how middle differs from low via beta 1, how upper differs from low via beta 2. Now, a quick review. When I say I made low the reference, how do I know that? How do I do that? In a coding scheme, how would I know that low is my reference? Yeah, I'll take gestures. Yeah, this can be a gesture question. The 0, correct. Now, more specifically, what is 0? The intercept? The intercept refers to the group coded 0, but where do the zeros go?
Which does not reverse to.
Yeah, so what I'm asking then is where 0 goes is in making these variables. Let's check it out. Say we'll look at the R code for this. Here's the code that created those two variables. And the one group, which stands for low, is coded 0 for both of my new variables right here. So by setting the low group as 0 in both places, that means that the intercept of the model is going to refer to the low group because the intercept refers to when all the predictors are 0. And then each of the other variables that I've created, L versus M and L versus U in this case, are going to say how the other group differs from low. Cough, cough, homework question. I'm saying it that way deliberately. The slopes tell you how the group coded 1 differs from the group coded 0. And direction matters because otherwise the inference would be backwards. So if beta 1 is positive, that tells me that the M group is higher than the L group in my coding scheme. If beta 1 were negative, that would mean the low group is the higher of the two. M is less. So these two are working together to describe differences in income across this 3-category predictor variable. These two right here, beta 3 and beta 4, are working together to describe a quadratic effective age, so a U-shaped function, either up or down. Beta 5, 6, and 7 are then working together to describe piecewise slopes of education, where 11th grade education is my reference for those. That's when all three of these are 0. Beta 5 is going to track the effective education from 2 years to 11 years. Beta 6 tracks it from 11 years to 12 years, and beta 7 tracks it over 12 years. And in talking about what each of these slopes mean, the other piece of this that changes is the idea of after controlling for. So for instance, this is the effective education after controlling for age and self-rated working class. This is the effective age after controlling for education and working class. And this is the effective working class after controlling for age and education. So each of these predictors is only going to get credit, so to speak, for what it brings to the prediction of income uniquely that the others do not. So that means there's multiple ways that we can talk about effect size for these slopes and its contribution to the model in more of a standardized way. And that's what we get to talk about today. We started going over it last week, but it's sufficiently complex that I think it would be good to do it again. So any questions on any of that so far? All right. So then I have a bunch of code here designed to not just estimate the model, but to tell us the extra pieces of information that we would want to know about how the slopes that pertain to the same conceptual predictor work together to represent that predictor's contribution to the model predicting income. So to put all the slopes in the same model is probably what you would guess. You just list them all where the predictors go. So it looks like that in SAS. It looks like this in STATA. And it looks like this in R. A couple things that are a little bit different than before. In R, I ended up making an age squared variable as an observed variable for this analysis because it wouldn't let me use the squared term in a general linear hypothesis test, so I cheated and worked around that way. Otherwise, it is represented as a directly squared term, not in the data, but just in the model, in STATA by using the hashtag, and in SAS, the same thing happens with an asterisk. So the output that we get by default then differs by program, because SAS has this very nice option for effect size right here that is going to spit out semi-partial effect sizes and partial effect sizes for each individual slope. We have to work a little bit harder to get those in some of the other packages. The rest of this, though, pertains to additional information that I want to know given the context of this analysis. So first off, this estimate statement right here, this LinCom statement right here, and in R, it is this first chunk right here for mid versus upper difference. Those are all doing the same thing. What they are asking for is the difference between the non-reference groups. So the model tells us how mid differs from low, how upper differs from low. The model does not directly tell us how upper differs from middle. So that's what I'm asking for here. So in your homework instructions, I often say, make a point about this idea of this versus, and that the one before the versus is to be coded -1. This is what I mean. So it ends up with the direction of -1 first and 1 second, that this is going to tell us how the upper group differs from the middle group. If I switched the signs on these, I would get the exact same number, just with a different sign. So the inference would be the same as to whether the groups are different. It's just a question of the direction of the difference and who's higher. So I'm asking for this as an additional piece of information that I want to know because it contains the third difference that's possible for right here. There's no other differences like that I need to ask for with respect to the estimate statements, so I don't have other pieces of code. The rest of this, what it's doing is lumping together the fixed slopes that pertain to each conceptual predictor so that I can get a significance test for just that set of slopes and an effect size. So if I want to know, for instance, is there a significant effect of age? Age is represented by 2 slopes, so I want to lump them together to get the test for that. Likewise, is there a significant effect of education is represented by 3 slopes, so I need to lump those together. Is there a significant effect of working class is represented by those 2 slopes, and so I want to lump them together. So what happens in practice is that a lot of folks would do this as a stepwise regression. Like I might start with a model that just has these 2 terms in it, and then estimate a second model that adds the age terms so that I can look at the change in the R-square, and then estimate a third model that has these terms in it. And in fact, on your next homework, that's what I'm going to ask you to do, is to do it in layers like that. The reason for that is because of differences across packages and how easy it is to get a test for the R-square. I wanted to make it fair, and that way makes it the easiest to get it. However, doing it in layers then causes some interpretational ambiguity because you get a different conclusion. Say if you started with education and then looked at the change of R-square after adding age, than if you start here and add age. Does that make sense? The idea of which came first does make sense. Okay. All right. Let me help it make sense. How's that? And thank you for your honesty. I had like 4 people go, like, absolutely not, Lisa. That's informative. Let me pull up this slide here. So we talked about this last time. So this is an example of that sort of layering sequential model building strategy where I start with A, I can look at the R-square for the model with predictor A. I can add predictor B, look at the R-square for the model, and look at the change in the R-square. And then I could add in, say, predictor C and D, look at the model R-square, look at the change in the R-square. So what I'm about to demonstrate is how to get the information for this last column, the idea of how much of the R-square is due to the new terms you've added, but to not have to do it in a layered approach. Because what happens if this order makes complete sense to you based on the context of your study and the theoretical position that you have, but reviewer 2 comes along and says, no, I think C and D should have been first. And then you should have seen if B added to the model after controlling for C and D. Now, could they have a point? I think they could, in a lot of cases. There's very few situations in which it is unequivocal which comes first and which should be considered the new contribution. The way that this is often done in practice is that your lit review says, here's what we know about Y. This predicts Y, and this predicts Y. Here's all the studies that have found that. But no one's looked at this new shiny thing that I have, so I'm going to see if my new shiny thing adds to the prediction from what's known in the current literature. And that type of sequencing makes sense if everybody agrees on what the new shiny thing is versus what the old not shiny thing is. One person's control variable is another person's career. Think about it. Right, all the things that go into the front part of your lit review, we know this, we know this, we know this. At one point in time, we didn't know any of that. And so they had to demonstrate those new contributions in and of themselves. Now we're continually adding to it. So there's not necessarily always a clear, correct order as to how the model should be built. And if we have something like A is still significant after we add B, but it's not significant after we control for D and C and D, then how we talk about A changes as a consequence of finding that out. And we might end up with a different description of our conclusions if we added the predictors in a different order. Okay, does that help a little bit? Okay, that helps a little bit. No, I didn't say help. I said help a little bit. Hashtag goals. Help a little bit. So for your next homework, not the one that's due tomorrow, but the one that I'm working on right now, this is the kind of thing I'm going to have you do because it's the fairest way to equalize the work it takes across software packages. That's literally the only reason. In practice, what I would encourage you to do is to start with a model that has everything. Let all the predictors fight it out. And if you want to have questions about what do C and D contribute that A and B don't, you can ask for that as an additional piece of output. What do A and B contribute that C and D don't? You can ask for that as an additional piece of output. That's what I want to show you how to do. So in, where to go? For A, here we are. So in this model, for instance, I'm dumping in all 7 slopes representing 3 different conceptual predictors, and I'm letting them duke it out. Okay, questions about just that as a concept? So the output that we get by default then is the usual, let me see here, let me find it, the usual parameter estimates table. It's going to tell us what each fixed effect is, the intercept in each of these slopes. It's going to tell us what the standard error is. It's going to give us a t-value. Estimate divided by standard error is t. That tells you how many standard errors away from the null hypothesis that slope is. It's going to give you an exact p-value for if the null hypothesis were true, how often would you see a slope this big? And then it gives you a confidence interval using that same information. So what I'm talking about is extra, because I don't have an answer from just this output, for instance, as to what is the contribution of age. Like if I want to know that, I can't just like add these slopes together. I can't like combine these p-values in any sort of way that makes sense. I have to ask for that additional contribution because these 2 slopes have a variable in common, age and age squared. So I need to account for their covariance between the two as part of the contribution of what they bring to the model. Likewise, these have a common reference group. They'll have covariance as well. So I have to ask the software to give me a custom f-test for multiple slopes and a custom set of effect sizes to go with multiple slopes as well. And this is where the labor involved in this differs across programs. So in SAS, to start with, the new command that you have to get to practice in your next homework is called contrast. Contrast is a way to lump together multiple slopes to get not only a significance test for their joint contribution, but also an effect size via this handy-dandy option right here called effect size. The structure of this code, the word contrast is a recognized SAS command, that's why it's in blue. The stuff in purple is a label that's going to show up in your output. So you can write anything you want here, but writing as much as possible to help you remember what it's for is a good strategy. Because like you're learning all of this now, like what do you think would happen if you came back to your code a year from now? Would you know exactly what you were doing and why and how? No. Me neither. So there is a reason why there are so many comments in my code describing what is happening. That's not just for you, that's for me. So I would encourage you to make use of commenting features as well as these sorts of titling features to leave yourself a trail of breadcrumbs as to what this is doing and how and why. The first contrast in here is just for pedagogical purposes, okay? You don't need to do this. What I am trying to reproduce with this statement is the model f-test that is already given to you. In this class, using general linear model software routines, this will always be given to you by default. In any of my other classes, it will not. So knowing how to ask for it is a useful tool for those future situations. But the way that these statements work is you list the slope that you want, followed by a 1, separating them by commas. The commas denote numerator degrees of freedom, so that it's going to treat this slope as separate from that slope, as separate from that slope, and so forth. It's not trying to do any math to add them together. So by listing all 7 slopes, what this contrast is going to recreate is the overall f-test for whether my model R² is significantly greater than 0. The ones that I actually want, that are not just for pedagogical purposes, are the next 3. And each of these pertains to the grouping of fixed slopes that go with each conceptual predictor. So I'm grouping L versus M and L versus U because those combined tell me whether the effective working class is significant. I'm lumping together age and age² because those combined tell me about age. And I'm lumping together these 3 education slopes because they combined answer the same question about education. So this is extra information I'm asking. This is directly analogous to doing a model with all the things included and then taking something away and seeing what happened, or having a subset and then adding stuff to it. So this allows you to do the same kind of idea as the layered approach, but to do it all simultaneously. That way you do not have to worry about what would happen if you chose a different order of inclusion of your predictors. So this is the most conservative strategy with respect to making sure that you can say, here is the effect, and it doesn't matter what else is included because everything is included at this step. Okay, how are we doing? 1 thumb, couple thumbs. Okay, not very many thumbs. Thumb sideways? Okay, thumb sideways. That really needs to be an icon, doesn't it? It needs to be a thumbs down and a thumb sideways. So Zoom people, if you're listening, I mean, come on, it gives me like poop emojis, right? Like I can put a poop face on my head here, and it doesn't have thumb sideways. So, what good is that? By the way, this is called, at my house, moji poop. All right. So thumb sideways. Is thumb sideways because you don't know why I'm doing this or how the code works, or does anyone want to clarify the sideways? Or because I haven't done anything but SAS yet? That one? Fair. Fair. I know that most of you are only trying to learn one package, and it's the one that either your advisor told you to or the one that looked the easiest. But keep in mind that after you do this in one package, learning another one is much easier than learning the first one. And the more packages that you have, the more lines you have on your CV under technical skills. And the more different collaborators you can work with who have only pledged allegiance to one package. So I hope at some point that these resources of doing everything 3 times will be useful to you if you come back to it to try and pick up one of the packages that you aren't learning. Okay, fair enough. Then trying to resolve the thumb sideways because we haven't talked about the other programs. STATA's Lincom to get the missing pairwise difference. That's old news. You've done that several times before. The new thing are these test, and these are the analog to contrast. So it's test, and then in parentheses, you set each slope equal to 0. So the parentheses denote numerator degrees of freedom for this test. So the first one, again, pedagogical purposes to demonstrate how the f-test for the model R-square would be recreated. The next 3 do the lumping per conceptual predictor. So this is for working class slopes, this is for the 2 age slopes, and this is for the education slopes. Now, the pro to this, it gives you an f-test. So you can get the joint contribution and whether it's significant. The con, it does not tell you the effect size. You got to work a little harder for that. And then folks who are using R, as usual, it takes 37 lines of code to do the same thing that it takes 6 lines of code in another program. So we have the usual chunk here. So I think one of you said, are these like paragraphs before? Yeah, you can think of them as paragraphs because each one is like doing a different thing. So this is just spitting back the default model stuff. Residual variance from this piece of output, the summary of the model to get the fixed slope estimates, standard errors, and so forth, confidence intervals because that's separate. This chunk right here is getting the pairwise contrast for the non-reference groups for work class, middle versus upper. And note this bad boy right here. You look at that and you're like, where the hell did she get that from? This is in the order listed right here. So you have to check your output to make sure that it wrote them in the order that you did, because I have learned that it will sometimes rearrange it in certain circumstances. And then these coefficients apply just to the slopes that are in that spot. So this first 0 means I'm not talking about the intercept. The next 2 slopes are the 2 that I'm talking about, and I want the first one to be -1 and the second one to be 1. That gives me their difference. And ignore everything else. That's what 0 means. If you get an error message when you try this, it may be because you don't have enough digits. So if there's a mismatch between the number of fixed effects as given here and the number of values separated by commas, it will yell at you and not give you output. I have learned that the hard way several times. And that is the primary reason why there's a 1 here. So that I remember the first one is the intercept. It's not the first word I typed. So I'm asking for this additional piece of output, saving the summary of it, printing that saved summary, and the reason I'm saving the summary is so that I can compute effect sizes on it subsequently. Now the new ones. Same command, GLHT stands for General Linear Hypothesis Test, but a different syntax structure that actually works a little bit more transparently. So this chunk right here is the pedagogical purposes only, demonstrating how I would use this command to get an f-test for the R-square of the model with all 7 slopes. So each slope that you want included, you set equal to 0, put it in quotes, and separate them with commas. The commas denote numerator degree of freedom, just like in SAS. Then the summary with test equals F test tells it what kind of joint hypothesis test you can do. Your choices are F or chi-square. F is using denominator degrees of freedom, which is the better strategy, particularly if you don't have a lot of data. The next 3 then correspond to each conceptual predictor. So this one is for work class with just those 2 slopes in it. This one is for age and age squared. And this one is for education down here. So the numbers that I'm saving, the names here I should say, model 2 F for class is what that means to me. Because these are all coming from what I labeled as model 2. I'm doing this to get an F test, and the F test is for the effective class. This is model 2 F age. The F test for the effects of age, not to be confused with the yogurt that I eat for breakfast most mornings, which I call phage. I think you're supposed to call it faya or something like that. Any phage fans in the house? Yeah, you know what I'm talking about, right? It's Greek yogurt. It doesn't taste good, but you put enough stuff in it and it tastes better. So I put fruit and stuff in it. So phage, breakfast, slopes for breakfast. And then model 2 F for education is the one down here. So again, the reason I'm doing this is because I want to be able to talk about the combined effect of each predictor, and when a predictor is characterized by more than one slope, I got to ask for that joint test in addition to their separate slopes. That's why. Another way of thinking about this is that each of these commands here, where I'm testing just a subset of the model, what that F is referring to is the change in the model R square brought on by adding this set of slopes significant? This is an F test for the change in R square related to that joint contribution. To get an effect size for it, to get the actual change in the R square, we got to work a little harder. That output is still coming. Okay. Where are we at here? 236. Okay. How are we doing now? Sideways? Up? We have some what I call heterogeneity. Okay, questions that I can answer or clarify. All right, you want to see what we get? Sure. I think we get it. Did I do it in all the packages? I did. I did it in all 3 of the packages. Because it looks enough different in this case that I wanted you to be able to interpret your package. So in the same order, starting with SAS, then STATA, then R. So as usual, here's my first summary table for the overall model. So my F for the 7 slopes combined is 42. That F is significant. So the other way of saying that is that my model significantly predicts income. How good is it? Where do I look for that? R square, yep. It is about 29% good. Is that a lot? I don't know, it's 29%. What's the best it could be? 100, yeah. So it is what it is. Other way of thinking about this, how do I talk about this as a proportion? %29 of what? Explained, yes. So if all of the variance in income is our goal, I have explained 29% of it. That means that I have 71% left to go. If I want to talk about this as a correlation, This is the square of the correlation between actual income and income predicted by my 7 slopes, otherwise known as y-hats. So this is like a general, how good is my model? This much good. Then we get the breakdown that is specific to each individual slope. And this is the part where it starts to get a little bit tricky. So SAS gives you this handy-dandy table that has 4 separate effect sizes in it for each slope. Semi-partial eta square is the one that I'm highlighting. This is how much of the R square is due to that slope. So remember, I got 29% overall. In theory, I should be able to look down this column and talk about how much each individual slope created towards the R square. In practice, though, I can't do that for all the slopes. These two in particular, because they share a common reference group, I cannot add up their semi-partial R squares without taking into account their common variance. So I can't use these two. This one I can use, but keeping in mind that it's conditional on the slope at age 18, given the centering of this predictor and the quadratic term. These ones are all okay to use by themselves. So instead of referring to semi-partial eta squared per slope, because it only works in some cases, I'm going to do it for each predictor instead. So the results from my contrast statements then come next to help me do that. So the first one is the pedagogical one, F-test for the model with 7 slopes in it. The sums of squares created by those 7 slopes and the mean square that you get by dividing that sums of squares by 7 are the exact same thing as what we get up here, not a coincidence. Yep, hang on, there we go. And the F for that is the same thing that we get up there too. So the real reason to do this are these subsequent lines. So what this is telling me first is, hey, hang on. The 2 slopes for working class, their F is significant. So that does working class as a concept contribute significantly to my model R square? Yes, they do. How much? 4%. Does age as a concept with 2 slopes contribute? Yes, it does. How much? 8%. Does education with 3 slopes contribute? Yes, it does. How much? 8% also. So here's my overall model R square with all 7 slopes. Here's how much is attributable to each separate predictor. Note that those don't add up to the total. Do you remember why? We have overlapping data. Common, yep. The C part. And to the extent that these predictors are correlated with each other and that correlated part is related to the outcome, that does contribute to R square, but none of them get credit. So the overlapping part is responsible for the difference to get us up to the full amount. Now the other 3 columns here. Semi-partial omega square, that's next to it, that is what you use if you're reporting adjusted R squares instead. Partial eta square is a different animal. This does not have to do with the model R square. It's a ratio of that source of variance over that plus error. It's talking about how much variance that term is responsible for, discounting all of the other predictors, only relative to error. Personally, I have a much harder time conceptualizing that as a useful thing to know. So for my money, it's all about this first column here, semi-partial eta square, because that tells you how much of the R square is due to those slopes, which is a readily interpretable quantity. Then the rest of the output, here's the result from my estimate for my missing group difference. Here's my table of fixed effects. Would it be helpful to go through this? Or do you feel like you've got a handle on what to do with slopes? What do we think? Yes, please go through it. Okay. So the first line item here is an interesting result. Beta 0, otherwise known as my intercept or the constant, it's actually estimated at -3. So even though I went to the trouble to center all of my predictors so that 0 is a meaningful value, I still end up with a prediction that's out of bounds. So who is this the intercept for? Across all of my predictor variables, where is the "you are here" reference point of the data? Let's go through the list. Who's the reference for these two? The low group. So somebody who rated themselves as lower class. Who is age 18, and who has what level of education? It's 11th grade. So an 18-year-old who finished 11th grade and rated themselves as lower class is predicted to make negative $3,600 a year. That probably means that somewhere in my model I have a misspecification because the slopes are predicting impossible values. It could also mean that I need to create different slopes besides linear. We will talk about that a little bit in the very, very last unit, sort of what to do in such cases where it looks like something may have went wrong. But that's okay. For now, we can accept that as a weird result, but it doesn't change the interpretation of what we have subsequently. So each of these are indicator dummy-coded variables. They each talk about how the one group differs from the 0 group. Always, 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 how the one group differs from the 0 group. So then it just depends on what the coding refers to. This is the people who rated themselves as middle make $6,000 more than people who rated themselves as low. People who rated themselves as upper make $7,000 more than people who rated themselves as low. Both of those things are significantly positive, according to the p-value. Do I know whether or not there's a significant difference between middle and upper, just based on looking at this? The two non-reference groups, middle versus upper. Do I know about them just from what's in front of me here? Not yet. I had to ask for that. I can do the math in my head. It looks like the difference between those two groups is 1.2. 7.2 minus 6. That's what the estimate/lincom/GLHT statement is going to tell us, is to give me a standard error for that comparison. Linear and quadratic age then are next up. So this is my age slope. So for every additional year older someone is, they are predicted to make about $1,000 more. However, this is the slope specifically at the centering point for that variable given the quadratic term at age 18. So there's a U-shaped function here where people make the most money at middle age. So this is the positive slope on the lower side of the U, and it's going to be heading up and becoming less positive per this negative quadratic term. So what happens to this positive age slope as age increases is that it is becoming less positive. It's a positive slope that is slowing down. And do you remember the rule for how we interpret quadratic coefficients? There's one thing to get it right: we multiply by 2. Cough, cough, homework question. So twice this number is how the linear age slope changes per year of age. It's because this number is actually half the rate of acceleration or deceleration, so to get to the full rate, you got to multiply it by 2. It's the second derivative of the function with respect to h. The 2 comes down. So the pattern this is creating then is a u where the slope is slowing down and eventually tips over and goes negative. So that's why on your homework, I had it worded as one set of choices for less positive or more negative, because if you follow the curve as it's getting less positive, it eventually becomes negative, versus the other way, which is less negative into more positive. So it has to do whether the u is a frowny face or a happy face. This is a frowny face, except for people who are middle-aged, because they make all the money. And then each of these is a linear slope. So the first one talks about the difference in income per year of education for people who have less than a high school degree. So I would call this slope non-significantly positive. So income is predicted to increase, but not unexpectedly. So if the null hypothesis of zero slope were true, I'd see a slope this big like 64% of the time, not in unexpected territory. Likewise, this one, this is the bump you get for graduating high school. So it's from 11 to 12. So people who graduated high school make $3,000 more. And is this one significant according to this p-value right here? I'll let you think of that. I've got a question in the chat. Is the way to interpret that on homework 4 different because more is better rather than less, or is it interpreted by the negative either way? The shape of the U would be the same either way. Whether more is better depends on the direction of the outcome. Okay, so like in golf, more is worse. Okay, so we have, with respect to my question, is this a significant slope per this criterion here? I've got one vote for no, another shaking heads. What do we think? Thumbs up for yes, thumbs down for no. Yeah, or poop emoji for no, I guess, if that's what we're going to go with. Emoji poop for no. Yeah. It's so close, though. So this is where we get into euphemisms for non-significant but close. You will see people call this approaching significance or trending towards significant or marginally significant. All of those words. My favorite is approaching, because it makes it sound like if you just come back later, it will get there. Like a cake that's not done baking. Like, well, it's p equals 0.07. Give it another day. No. In the strictest sense, we decide our alpha ahead of time. At 0.05, this does not make the cutoff. This one does, however. So people who graduate high school, for every year additional education they get, they make $1,500 more. Now let's talk for a minute about this alpha cutoff. Alpha is type 1 error rate, right? Doing a little review here. Type 1 error is what? What's a type 1 error? False positive or false negative? False positive, correct. So if I set a type 1 false positive error rate at 5%, which is what 0.05 means, how many times out of 100 am I going to get a false positive? Not a trick. 5. In other words, 1 in 20. How many slopes do I have here? 7. So I'm judging each of these against a false positive rate of 0.05. That means that if I had 20 slopes in the model, I could expect one to be significant by chance. So this might make some folks uncomfortable. And this is where concerns about alpha inflation or experiment error rate come into play, is when you're testing a lot of things, people may want you to be more conservative than you would be if you're testing only a few things. So keep that in mind. If you have a lot of slopes to examine, you might want to pick a different alpha rate so that you're less likely to stumble into a type 1 error. Okay. Any questions on that? Okay, let's see what the other packages give us. So STATA's output then next is very similar to SAS. We get our summary table of the model over here, and we get our R squared and F information over here. STATA does you a solid by putting the degrees of freedom into context. So 7 is numerator degrees of freedom for the number of slopes. What's this one? The 726. Denominator. It's the number of slopes I could still add if I wanted to. It's n minus k. So this sample has 734 people. I lose 1 on the total here because the intercept is always included. So I could still add 726 more slopes. The slopes for STATA are always listed first, and the intercept is always listed last, and it's labeled as constant. Always. Here's the linear combination for the missing pairwise difference, how upper differs from middle. So the 1.2 I did in my head, I was pretty close to that. P-value not significant. Here's the new results. So STATA folks, you have not seen this yet. So these are the results of the test statements. So these, scrolling back, these jobbies right here, how you lump slopes together to get a joint hypothesis test for their contribution to the model R square. So it tells you which ones, repeats what you told it basically, and then gives you an F for that. So here's the 2 for working class, there's the F for that, here's the 2 for age, and here's the 3 for education. No effect sizes though, we gotta work extra hard to get those. And here's R. So one thing that I haven't talked about yet that is probably relevant is the rest of this. Ignore it. This table right here, ignore all those things if you're using R. That is a different way of computing sums of squares known as type 1 instead of type 3, which assumes that you're doing it sequentially on purpose. So the only reason that we are asking for this output right here is just to get this one number that's not provided elsewhere, which is your residual variance. That's the only reason I'm using it. Here are my coefficients. Intercept listed first, and then all of the others in order. And those exactly match what we get from the other programs. And then in the bottom here, it gives us the summary of the model. So the R square, adjusted R square, and the F test for the overall model, 7 slopes, and the p-value. Then the new pieces from the GLHT statements. Here is the pairwise difference for how the upper group differs from the middle group. That's you've seen before. The new ones then are the lumping of the slopes, and it looks a lot like the STATA output where it reminds you what you asked to lump together to test against 0. It gives you the F, the degrees of freedom, which is the number of slopes that went into the F. The denominator degrees of freedom is the same as the model, and then the p-value that goes with it. This is scientific notation, by the way. It means that it is 0 to 50 decimal places. Here is the F test for the 2 slopes for working class. Here's the F test for the 2 slopes for age. And here is the F for the 3 slopes that go into education. So on your next homework, I'm going to be asking you to provide these F tests. This is the one new piece of code that you'll need for the next homework, just this. To get the corresponding actual change in the R square, I'm going to have you do it sequentially so that you can just look at the difference between what the R square was from the previous model and what it is after adding stuff. That way everybody gets to do the same amount of work. Okay. Any questions on code or concepts thus far? All right, so then I have a summary here of what happened with respect to the full model and then the pieces of the model for each variable, the semi-partial eta squared that went with each piece, and the partial eta squared. And then here's the missing pieces. So these two columns right here were given directly by SAS and not the other programs. What I got from the other programs were F-tests that told me whether they were significant, but not what they were. So the rest of this is the extra work that we would have to do to get the amount of the R square that is attributable to that set of slopes in a same model. Question, what if your p-test result is less than 0? Then it's really significant? Is that what you mean? If it's significant or not. If it's less than your alpha level, it's termed significant. Yep. Some people would like to use really, really small p-values as some kind of index of effect size, but they're still not. Because you can have a significant result because you have a large effect or a large sample or some combination thereof. So effect sizes are still a separate animal. So here's how we get them in the other packages. So if I want to know how much of the model R square is due to the two slopes for working class, then what I have to do in both STATA and R, so I've got both of them here, is get the total sums of squares. So that's the same across models. That actually comes from the empty model. So in R, I saved that number as an object. So here's R code for an empty model for this outcome, which I didn't have in the handout previously. And I am saving that number right here for the total sums of squares as an object called SS total, so I can use it in my math. So in STATA then, what I'm going to do to figure out what is the contribution of the working class slopes is estimate a model where they're not included. So I kick them out. And I see by how much the model sums of squares for explained information goes down. And I put that in my formula. So this sequence, I should say, is on slide 29. That's where this goes with. That's what I'm talking about. So I have my sums of squares for the full model with all 7 slopes. That's the amount of information in my outcome variable that those slopes have accounted for. I'm going to subtract from it the sums of squares for my reduced model, which has everything except working class. So the difference in this numerator right here tells me the unique sums of squares that come from my 2 working class slopes specifically. And then I can divide by the total sums of squares, which is the same either way. And the number I get back then is the semi-partial eta square for those 2 slopes. So bigger picture, what this number means? Hey, how much did the R square increase if you add these 2 slopes? That much. Because here's what it is in the full model with them. Here's what it is without them. So the difference of these 2 numbers has to do with the 2 slopes that aren't in this current model. So how much of the sums of squares is accountable to those 2 slopes divided by the total sums of squares? That's semi-partial eta square. So that 0.04 is the same number that was given directly by SAS several pages ago, right here. It does it for you. Likewise, in R, I estimated a model without those 2 slopes. I then computed the sums of squares for that model, and I took that sums of squares and divided it by the total, and I got the same answer. Okay, so those of you who are going to be using STATA or R, you don't have to do this for me, okay? This is for the rest of your life. because I don't want to make it so that people who are using one package have to do more calculations than someone who's using a different package. So I'm not going to make you do that. But because I think this is the best way to do it, I wanted to show you how to do it. So what you're going to do is add in slopes sets at a time so that you can look at the change in the R-square, and you can do that with your calculator. You don't have to compute any sums of squares, anything. This is how we do it with the simultaneous analysis. Same thing for age. I estimate a model that has everything except age. I get the sums of squares for it. I figure out what the difference is relative to the full model and divide by total. So that 8% is what is contributed to the R-square by the two age slopes. Same idea in the R code. Estimate a model without age, compute the sums of squares for that model, and divide the difference here by the total. And then here's education. Same thing, model without those three slopes, difference in sums of squares, divide by total. Ta-da. All right, and there's a comparison of what we end up with. This is an Excel table, by the way, that's in your download packet. Note the last two columns. Darn it, come back up here. These two columns right here, D and R, those are per slope effect sizes. So those are just computed using this t-test statistic and denominator degrees of freedom like you've been doing in your homework, because I think it's useful to supplement semi-partial eta squares for the overall contribution of the model for each predictor with the specific partial effect size for each of these things. So I'm using each of these distinct effect sizes in a different way. These individual D's and R's do not refer to how much of the R-square at all. It's just an effect size for that specific slope's unique contribution relative to error. And that's why we can talk about these only using the t-test statistic. So these can be easily computed from your t output in your programs, and that's the code that I gave you in example 3, and there's code online to do it for this handout as well. I just didn't repeat it in this case. So the results section then illustrates how I would talk about all of these different effect sizes at the same time. So we have, first off, what happened to the model? Model with the 7 slopes, significant. Here's my R-square. Here's what happened for each of my individual predictors and their partial effect sizes. So I would put a table of estimates. I also have a comparison for what it was in the bivariate versus this to demonstrate the idea of differences in effect sizes after you control for other predictors. I would add this to the table note, by the way, in case there's any question about where those effect sizes come from, give them the formula. Then they know exactly what you did. So in addition to how well did the overall model do, how well did each individual slope do, significance test and effect sizes, then I'm also talking about each conceptual predictor as a collection of multiple fixed slopes. So this paragraph is about working class. The omnibus, that means altogether again, that's an ANOVA phrase. Unique effect, meaning after controlling for the other predictors in the model. Effect of 3 categories self-reported working class remains significant after controlling for other things. So then this is the extra piece that I just had to go to a bunch of work to get. The F value for those 2 slopes in particular comes from contrast in SAS, test in STATA, and then the GLHT setting the slopes equal to 0 in R. And then to get the semi-partial eta square that goes with it, I get that directly out of SAS. I get that from the other programs by taking the slopes out of the model and seeing what happened. And then I can talk about the pattern of the results. So these are the differences of how middle and upper differ from low. And then I mentioned the third comparison as part of my results. Then I have the same structure of the paragraph with respect to age. So I talk about the contribution of age to the model, of the model R-square. Age is responsible for 8% of it. And then we interpret the coefficients. And then I talk about the 3 slopes for education. Their contribution to the R-square was also 8%, and then talk about that stuff. So one thing that I want to mention with respect to all of these results sections, if this is all you put in a manuscript, it will probably be rejected. This is technical documentation describing the results of a model, but what is missing from this is as expected from research question 1, or as found in previous research, or in contrast to what so-and-so found. All of the context about why these variables are in your analysis, what you want to know about them, and why somebody should care. All of that additional context has to be interwoven to these sentences. So like this just tells me that these two slopes contributed significantly. Why should your reader care about that information? That's on you. So this should be tied to research questions, it should be tied to hypotheses, and the more you can do to put it into context, the more your reader will follow you. So I have this sort of a generic note about that the rest of this I can't give you a template for because it's context specific. This is just how you would talk about the numbers in your output. And that's the end of that. Okay, any questions? Well, this process and logic is the subject of one of the questions on your next formative assessment, which is due next week and is available to be started whenever you'd like. So you'll get a chance to think this through, and we'll talk about that next week as well. Looks like we're going to do the next example and the rest of the lecture on Thursday. So then we will wait to do interaction terms starting next week probably. That's fine by me. Yeah, I think that's all I had to say about that. So anything else you want to talk about or ask me about before we call it a day? No? Okay, then what we'll do next time is talk about some interesting regression results where things don't turn out as you would expect and why that is, and then another example using a different data set, just walking through this process again, and how I would combine separate analyses and multiple analyses to try and figure out what the story is with respect to a bunch of predictors. So we'll do that next time. Okay, then let me know if you have need help with your homework due tomorrow night. Office hours start at 3:30. Thanks for being here. Happy Garbage Day. See you next time.
Thank you.